BTEC Applied Science for AAQ, and this is my first chemistry video. Yay! So, Unit 2, which is chemistry, and this video is about the periodic table. So we're really going to dig into the basics, the stuff that you should really know from GCSE, but don't worry, it's going to get a bit fruitier later on. Here we go. So that's the periodic table. The periodic table of the elements. What are elements? Why are they arranged this way in this table? And what do the numbers mean? There's a small number and a big number. Sometimes the big number's on top and the small number's on the bottom. It doesn't matter. There's a small number and a big number. Anyway, so first of all, what are elements? Well, there are 94 naturally occurring elements, okay? Sodium, carbon, chlorine, helium. These are elements. Now, what is an element? Well, an element is a substance that is made from one type of atom. So, how many types of atom are there? And the answer is 94. There's 94 types of atom. And an element, such as gold, is made of gold atoms. Lots and lots of gold atoms and nothing else. Oxygen is made of oxygen atoms. They happen to be stuck together in pairs, so it's actually oxygen molecules, but it is just one type of atom. Aluminium is made of aluminium atoms. Okay? They used to think that water was an element, but now we know it's not. Now we know it's hydrogen and oxygen, isn't it? H2O. But an element is a substance made of one type of atom, and there are 94 naturally occurring elements. We're not interested in the other half dozen or so which aren't naturally occurring. Now, elements can chemically combine to form compounds. So not just mix together, but actually something's happened to the electrons on the outside and they are chemically combined into compounds. And there are two types of compound and they are called, and I'm sure you know the answer, they are covalent and ionic. And we'll talk a lot about these in other videos. So covalent compounds sharing electrons, the atoms share electrons. Ionic compounds is when they swap electrons. You know, one element gains, another element loses. They swap electrons. Now, in the periodic table, why are they in that order? First of all, why is hydrogen first? Hydrogen, helium, lithium, beryllium. Why are they in that order? And the answer is that they are in order of mass. So hydrogen is the lightest, and then helium, and then lithium, and then beryllium, and then boron, etc., 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 all the way up to plutonium. Yes, so they are in order of mass, okay? And then they are in groups, and they're in groups depending on their properties. Now, hydrogen's a bit of an odd bod, and I draw it on its own because it's not really, well, it is in group 1, but it's not one of the group 1 metals. The group 1 metals, lithium, sodium, potassium. And way over on the right, we have these helium, neon, argon. They've got similar properties. So elements in the same group have got very similar properties. And that's why Mendeleev put them in those groups. And then going down, we have period 1, which is just hydrogen and helium, and then period 2, period 3, period 4, etc. So groups and periods, and that all is to do with their properties. It's why they're called a periodic table, because periodically, the same properties keep on turning up. I'm sure you know the answers to these questions. Which group contains very unreactive gases? Which contains very reactive metals? Whereabouts are metals in the table? And you know that the unreactive gases are group 0, not group 8, group 0. yeah, the noble gases. Very reactive metals, we're talking group 1. Group 2 metals are pretty reactive as well, but group 1, lithium, sodium, potassium, rubidium, cesium. Metals are on the left-hand side. Okay, in fact, about 3/4 of the elements are metals, and they're way over on the left. The non-metals are kind of on the right, kind of top right cornerish, the non-metals, apart from hydrogen. It's a bit odd. Blocks, we'll worry about blocks later, SPDF and all that. When we've done loads of stuff about electrons, we will understand blocks. But we can, in the periodic table, divide it up into these blocks as well. And as I said, it's to do with electrons. Now, what do the numbers mean? Well, you've got the small number, and it's basically where the element is in the table. It's called the atomic number. So from hydrogen, hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, ... plutonium is 94. Yeah, we'll worry about protons in a minute, okay? But basically the atomic number is where it is in the table. They're in order of mass, and so number 1 is the lightest. The big number is called the relative atomic mass. You know, we might abbreviate that to RAM later on, the relative atomic mass. And it's basically the mass of the element compared to the other elements. Okay, I mean, hydrogen is number 1, helium is number 2, but a helium atom is actually about 4 times heavier than a hydrogen. Okay, a carbon atom is about 12 times heavier than a hydrogen atom. So the big number is the relative atomic mass, and it's the mass of the element compared to the other elements. Yeah, in fact, it's actually compared to, if we say carbon has a mass of 12, then it's compared to carbon, or at least compared to carbon 12 anyway. Now, all atoms are made up of just 3 types of particle. So subatomic particles, yeah, things that atoms are made of, subatomic, and they are protons and neutrons and electrons. The protons and the neutrons are in the bit in the middle, and the Latin word for bit in the middle is nucleus. So the protons and the neutrons are in the nucleus, and then the electrons, we can imagine them for the moment whizzing around the outside, like in orbit, like kind of the planets going around the sun, something like that, yeah, in orbit. Protons and neutrons are heavy, okay? In fact, most of the mass of the atom, nearly all of the mass of the atom, is the mass of the protons and the neutrons. Protons and neutrons have, as near as damn it, exactly the same mass. Yeah, it's actually slightly different, but we'll say they have the same mass, and they are heavy. Electrons are very, very light, whizzing around the outside. Okay, protons are positively charged, neutrons are neutral, and electrons are negatively charged. Protons and electrons have the same amount of charge, only protons are positive, electrons are negative. Now, the small number is the atomic number, I've already said, and that's basically where the element is in the table. It's also the number of protons in the nucleus. So, I mean, it was the atomic number before protons were discovered, but now we know that it's also the number of protons in the nucleus. So carbon has got 6 protons, helium has got 2 protons, copper has got 29 protons. You notice the last 2, I put the little number at the bottom. You might see that maybe I should have done it the other way around, but it doesn't matter. The small number is the atomic number, the number of protons. In physics, we call it the proton number in A-level physics. Now, for a particular isotope, the big number is the mass number. So it's the mass number. I'll explain isotopes very soon. The big number is the mass number. And the bigger that is, then the heavier the atom is. It's the number of protons and neutrons in the nucleus. So the small number is the number of protons, and the big number, the mass number, is the number of protons and neutrons. So if you take away the atomic number from the mass number, that will tell you the number of neutrons. How many protons and neutrons do each of these isotopes have? Work it out for yourself. The answer is, so carbon, 6 protons, 6 neutrons. Helium, 2 and 2. Copper, 29 protons, 35 neutrons. The uranium, 92 protons, 143 neutrons. You'll notice as the atoms get bigger and bigger, as the nuclei get bigger and bigger, you actually need more and more neutrons. They're a bit like super glue holding it together, but that's physics, that's not chemistry. Chemistry is just to do with electrons, basically. Anyway, moving on. Now, this diagram represents a boron atom. Yes, so hydrogen, helium, lithium, Harry Henry likes beer, beryllium, boron. So number 5, atomic number 5, so 5 protons, 5 electrons. Looking at it there, you'll see the 2 electrons in the first shell, 3 electrons in the second shell. Yes, atomic number 5. Now, boron has an atomic number of 5. All boron atoms have got 5 protons. Yes, if you've got an atom which has got 5 protons, it's boron. Now, all borons, if it's neutral, then it's got 5 electrons in orbit. If it starts losing electrons, then it becomes a boron ion. Yes, I-O-N, ion. But this is just a neutral atom, 5 protons, 5 electrons. How many neutrons does a boron atom have? Well, 80% of boron atoms have got 6 neutrons, and 20% of boron atoms have got 5 neutrons. So they don't all have the same number of neutrons. About 80% of them have got 6, and about 20% of them have got 5. So, look at that. About 80% is 511, yeah, and about 20% is 510. So these are still boron because you've got 5 protons, but you've got different numbers of neutrons. And these different types of boron are called isotopes of boron. Yeah, these are the 2 main isotopes of boron. There's actually a couple of others, but they're very rare. These are the 2 main isotopes of boron. They've got exactly the same chemical properties, only the boron 11 is going to be heavier. It'll be heavier because it's got more neutrons. Okay, so this 20%, 80%, that's the relative abundance. That should be pretty self-explanatory. The relative abundance. 20% of it is boron 10, 80% of it is boron 11. Okay, now in the periodic table, what it says, if we look at the big number, it says 10.811. Now, what is that? Well, it's an average, but it takes into account the relative abundance. So if you're going to work out an average and there's 4 times as many of the boron 11, then the average is going to be closer to 11 than to 10, isn't it? Yes? So in the periodic table, what we call the relative atomic mass, yes, not the mass number, the relative atomic mass is an average for the different isotopes, but it takes into account the relative abundance of each isotope. Look at this now. This will make sense in a bit. Imagine you had a collection of fruit. This isn't something that I personally do, is collect fruit. I'm sure some people do. And let's say you've got 80 apples and you've got 20 pears. And the apples, each of the apples has a mass of 11, and each of the pears has a mass of 10. Looks pretty similar to boron to me. Anyway, what's the average mass of a fruit? Well, just looking at it, you'll see that the average mass is going to be closer to 11 than it is to 10, isn't it? Can we work out the average mass of a fruit? Well, look at this. So the average mass is going to be the total mass divided by the total number. In this case, the total number is 100, isn't it? 80 apples and 20 pears. So what's the total mass? Well, so we've got 80 apples, so 80 times 11 and 20 times 10. Yes? So that's the total mass. Add them together, divide by 100, and you get 10.8. Yes? If you want to go back in the video, look at the relative atomic mass of boron. Ooh, it's starting to make sense now, hopefully. Here's one for you to have a go at. This is a calculation that you have to be able to do. Okay, it's getting a bit mathematical now, but tough, you need to be able to do it. Chlorine has got two main isotopes. There's chlorine 35 and chlorine 37. Yeah, these are the mass numbers of the different isotopes, by the way. Chlorine 35, chlorine 37. About 75.8% is chlorine 35, about 24.2 is chlorine 37. Can you work out the relative atomic mass of chlorine? Pause the video, have a go, get your calculator. Yes, you should make best friends with your calculator. I'll show you the answer in 3, 2, 1. Okay, just as before, the average mass is the total mass divided by the total number. The total mass, so 75.8, yes, out of 100 is times 35. 24.2 out of 100 is times 37. Divide by 100, because I said out of 100, and we get 35.5. And if you want to have a look on the periodic table for the relative atomic mass of chlorine, then to 3 significant figures or 1 decimal place, there you go. Now, calculating relative abundance. This is a little bit trickier. We know how to calculate the relative atomic mass, but this is something else that you need to be able to do. So if we know the relative atomic mass, let's say of lithium is 6.93, and we know that it's got two isotopes, lithium-7 and lithium-6. This will be the information that you're given. Calculate the relative abundance of each of these isotopes. Before we do it, I'll ask you a question. Which isotope do you think is more common, lithium-7 or lithium-6? And the answer is, well, it's going to be lithium-7, isn't it? Because the relative atomic mass is a lot closer to 7 than it is to 6. So the lithium-7 is going to be more abundant. Anyway, how do we work out the relative abundance of each? I'll talk you through this one. Let's have a go. So the average mass is the total mass divided by the total number. Okay, we'll say that the total number is 100 because then it's all percentages. Yes, out of 100. That's what percentage means. So this time, now the relative abundance of lithium-7, I'm going to call that R. And then the relative abundance of lithium-6, that's going to be 100 minus R, isn't it? You know, so that's 100 minus R, because it's out of 100. Now, looking at the equation then, the total mass will be R times 7 plus 100 minus R times 6. And then you divide that by 100. Okay, and let's have a look. And that equals 6.93, because that's the relative atomic mass, 6.93. So work out the top. So 7 times R, so that's 7R. Multiply out the bracket, so 6 times 100 is 600, minus 6R, and then the 100, I brought that up to the right hand side, so my 6.93 becomes 693. So 7R minus 6R, and then you can bring the 600 over the other side, and we get that R is 93. So R is 93%, and so 100 minus R is going to be 7%. So there you go. Lithium 7, 93%. Lithium 6, 7%. Here's another one. Maybe you want to have a go at this one yourself. The two most common isotopes of neon are neon 20 and neon 22. The relative atomic mass of neon is 20.18. Use this information to calculate the relative abundance of the isotopes. First of all, I'll ask the same question I asked before. Which do you think is more common, the neon 20 or the neon 22? And hopefully you figured out that the more abundant one is going to be the neon 20, because the relative atomic mass is closer to 20 than it is to 22. Anyway, have a go yourself, and I will show you the answer in 3, 2, 1. So average mass, total mass divided by total number. Let's call that 100 because it's percentage. Here we have R times 20. So that's the neon 20. 100 minus R, so that's the neon 22, times 22 divided by 100. And we know that that's 20.18. So multiply it out. Yes. So 20R plus 2200 minus 22R is 2018. So R is 91%. So 91% is neon 20, and that means that 9% is neon 22. So well done if you managed to do that. Be able to do it might be in the exam. Key points. Elements are substances made of one type of atom. The periodic table shows all the elements in order of mass, and they are in groups based on their properties. All atoms of the same element have the same number of protons. Atoms of the same element can have different numbers of neutrons, and they're called isotopes, isotopes of the element. Looking at the numbers, the small number is the atomic number, and that's the same as the number of protons. The large number in the periodic table is the relative atomic mass, and that's the mass of the element compared to the other elements. Yes, it's actually compared to carbon-12, but compared to the other elements, taking into account the relative abundance of the different isotopes. Okay, you might be asked to calculate the relative atomic mass. You might be asked to calculate relative abundance.